Welcome to the flock. Let's dive into the concept of Boyle's and Charles' gas law by solving problems just like this one. Stick around to see how it's done. Now, before we can solve that problem, we need to understand what Boyle's law is even talking about. We're going to assume that the amount of a gas and the temperature of a gas are remaining constant. Then we can say, if those are the cases, that the pressure and the volume will vary inversely. That means that as the pressure goes up, the volume will go down, and vice versa. If the volume goes up, the pressure will go down. And we can represent this concept by using a mathematical equation where the pressure initially, P1, times the volume initially, V1, is equivalent to or equal to the pressure afterwards, P2, times the volume afterwards, V2. Now, if we have any three of these, for example, we can solve for the fourth variable, which would be like our x variable in math. Usually the tricky part there is identifying what word is what variable. In order to do that, please watch my gas terms and variables video, linked in the description below. So what does this concept look like? Let's see it with an actual balloon. This balloon currently has a specified volume. If I was going to change that volume by, say, compressing one end of the balloon, we can clearly see that the pressure goes up on the other side of the balloon as the latex expands. Now, anybody that's played with balloons before knows that if I was to continue compressing this area of the balloon, making the volume smaller, we would see that the pressure would continue to rise until eventually this balloon would pop. This is a classic example of decreasing volume to increase pressure, that inverse relationship. Now that you know what Boyle's law is, let's try the calculation. Synthetic diamonds can be created by using pressures of 6 times 10 to the 4th atmospheres. Atmospheres is a unit of pressure. Now, this is a huge amount of pressure, mind you. Standard pressure is 1 atm. This is 6 times 10 to the 4th. That's 6 with 4 zeros after it. 60,000 atmospheres. That's a lot of pressure. Pressure pushing down on me, pushing down on you. Anyways, back to the problem. So for this problem, if we took 2 liters of a gas, now 2 liters, that is a unit of volume. And that gas happened to be at the standard pressure of 1 atm. Again, that's a pressure. And we compressed that gas to the 6 times 10 to the 4th atms. That's also a pressure. What would be the new volume? So now we've identified which one's the P's and which one's the V's. Let's figure out which one's 1 and 2. Our initial volume is that 2 liters, so that's our V1. And our initial pressure is that standard pressure, P1. We're going to compress it to a P2 of 6 times 10 to the 4th atmospheres. Therefore, we are solving for V2 in this calculation. V2 is going to be our x. Let's fill in the spaces. All right, now all we have to do is plug and chug into our P1 times V1 equals P2 times V2 equation. Let's take our P1, that's 1 atm, and we're gonna multiply that by our V1, that's 2 liters. We're setting that equal to our P2, which is 6 times 10 to the 4th atmospheres, times x. That's what we're solving for. Now, our objective here is to get x alone. So just like in math class, when we have multiplying on one side, to undo the multiply, we have to divide. So we're going to divide off both sides by 6 times 10 to the 4th power, because what we do to one side, we have to do to the other side. Got to hold true to our math laws now. So essentially what we're doing is 2 times 1 divided by 6 times 10 to the 4th power, which in your calculator is easier to plug in as 6e4. So if you did it right, you should be getting 3.33333 times 10 to the negative 5 liters. In other words, if we took 2 whole liters of a gas and compressed it to that huge amount of pressure, we get a very, very tiny amount of volume at 3.33 times 10 to the negative 5 liters. Again, that's a very, very tiny volume of gas. Check your understanding here to make sure you did your math right. It would make sense that if we increase the pressure substantially, that the 2 liters of gas we started with should decrease. Remember, this is an inverse relationship. As one goes up, the other goes down. This also only holds true if the temperature is constant. We can't just take the same experiment and take it to Alaska and expect the same results. The temperature is going to vary vastly between here in Virginia and Alaska. So we can say then that Boyle's law is only going to be maintained or held true if the temperature is held constant. We can also represent this concept using a syringe and a little marshmallow. If we plug the bottom of this syringe, we can then say that the gas molecules inside the syringe are remaining constant. And if I decrease the volume by pushing down on the top of this plunger, we can see that the pressure will increase inside the syringe, therefore making the marshmallow shrink. Likewise, if we now release that pressure by letting the plunger up and increasing the volume, the marshmallow will grow bigger in size once again. Now that you've seen me do it, go ahead and pause the video here to give this Boyles Law calculation a try on your own. If you did it right, you should have gotten a V2 of 0.18 liters. Again, check your understanding here. We started at 300 millimeters of mercury for our pressure 1, and we increased the pressure to 500 millimeters of mercury. If we started with 0.3 liters of gas, it would make sense that by increasing the pressure, our volume would need to decrease. 0.18 liters is smaller than 0.3 liters, so we know we must have completed this correctly. In terms of looking at data, if you were going to plot volume on the y-axis and pressure on the x-axis, you would see an inverse relationship symbolized by a curved line. So if you were ever to do a lab experiment, for example, and you end up with a curved line, that's an inverse relationship between volume and pressure, meaning it would have to be Boyle's law. Let's move on to Charles' law then. If we're assuming now that the pressure of a gas remains constant and the amount of gas present remains constant, we can say that the volume and the temperature in Kelvin is going to vary directly. That means that as volume goes up, temperature goes up. You could also say that as temperature goes up, therefore volume goes up. And if temperature goes down, volume goes down. We represent this relationship with math by saying V1, our initial volume, divided by our T1, temperature initially, in Kelvin, not Celsius or Fahrenheit, is equivalent to our final volume divided by our final temperature. Again, in Kelvin. This is super important. Never calculate with the degrees Celsius or degrees Fahrenheit. You will get the wrong answer and be sad. Always in Kelvin. Remember, you need to add 273 to the degrees Celsius in order to calculate Kelvin. So what does this look like? Let's ask NASA. As you can see here, according to NASA, as the temperature increases, so does the volume of the gas. And as the temperature decreases, the volume drops back down. And when we plot that on a graph, we see that it's a straight line, indicating a direct relationship. As one goes up, so does the other. As one goes down, so does the other. When I put this balloon in the freezer about an hour ago, it was measuring at a circumference of 23 inches. And currently it is at around 22 inches. So since it was in the freezer where it was cooler, the temperature went down and so did the volume. This is an especially fun concept to try if you happen to have liquid nitrogen laying around. Let's try a calculation using Charles' law. The temperature inside a typical fridge is around 4 degrees Celsius. If I were to place a balloon with 0.5 liters of gas and an initial room temperature of 22 degrees Celsius into that refrigerator, what would be the new volume? Now remember, Charles' law is using temperatures in Kelvin. So we need to first convert these temperatures before we do anything else to Kelvin by adding 273 to the value in Celsius. 273 plus 4 gives us 277 Kelvin. And 273 plus 22 degrees Celsius gives us 295 Kelvin. Why do we have to convert this to Kelvin anyways? Hopefully you recognize that we are dividing, and you can have 0 degrees Celsius, but you cannot have 0 degrees Kelvin. You can't divide by 0 in math, which is why we have to convert these Celsius degrees to Kelvin before calculating. I see here 0.5 liters, that's a volume measurement, and that volume is going to be our initial volume. It's initially at a temperature of 295 Kelvin. So that's going to be our T1. Our T2 is going to be in the fridge. And so here we're solving for our V2. Now that we've identified the variables, let's plug and chug into Charles' Law. All right, to solve for x in this circumstance, we are currently dividing, so to undo division, we need to multiply. We're going to multiply both sides by 277 over 1. This means that top and bottom can cancel and we can get x alone. So essentially what we're doing is either dividing 0.5 by 295 and then multiplying that all by 277, or taking 277 times 0.5, dividing that value by 295. Either way, you should get x is equal to 0.469 liters as our V2 answer. Let's again check our understanding here. We know that Charles' Law is a direct relationship. So as the temperature goes down, the volume should also go down. We started with 0.5 liters of gas, and we do see that as the temperature went down, we got a smaller volume of gas. That means we did it right. Remember that Charles' Law can only hold true if the pressure is held constant. Now that you've seen me do it, go ahead and pause the video here to see if I'm full of hot air. Hopefully you got 2.35 liters as your new V2 volume. Make sure you always check your understanding to see if it makes sense conceptually. Here, we started at 18 degrees Celsius and we increased temperature. We know that Charles' Law is a direct relationship, so as temperature increases, the volume should also increase. Since we started at 2.2 liters and we ended up with 2.35 liters, we know the volume increased, we know we did it right. As I mentioned earlier, you can plot this experimentally as well, with volume on the y-axis and temperature in Kelvin on the x-axis. If you happen to see a straight line, you know that that's a direct relationship, and because it's involving volume and temperature, indicative of Charles' Law. Before you move on to the next gas law in this chemistry gas law series, make sure you can acquire the correct answer, given here. Also, if you're up for a silly challenge, try and figure out how many students would it take to raise the science classroom by 1 degree Celsius using only their farts? If you happen to figure it out, comment the answer below. In this lesson, we went over Boyles' Law, which relates pressure and volume in an inverse relationship. When pressure goes up, volume goes down. When volume goes up, pressure goes down. We also talked about Charles' Law. In Charles' Law, we're going to relate volume and temperature in a direct relationship. That means that as volume goes up, temperature goes up. As temperature goes down, volume goes down. And always remember that if you're calculating for gas laws using temperatures, they need to be in units of Kelvin. I heard somebody finally made it to 0 Kelvin, but they're okay now. Please give this video a quacks up and subscribe to Duckonta for some more gaseous content.
No ducks, no glory.